The picture depicts planet Earth and man, the Lord of creation, standing on land. Water runs off to the oceans under his feet as he racks his brain over the causes of climate change and disasters he must face with increasing frequency. Droughts, floods, landslides, streams dry up, river and groundwater levels drop, landmass overheats, atmosphere overheats. Here is a graph of climate change effects. In this NASA animation, which illustrates temperature measurements between 1880 and 2011, reds indicate the mean air temperature rise since 1850. If the temperature around the equator rises by 0.6 degrees Celsius, the temperature at the North Pole increases several-fold. In this graph, blue illustrates the minimum water levels of the Uch and Tisa rivers in millimeters since 1956 and the parallel estimated drop of the groundwater levels. Some sources claim that the greater vaporization brought about by climate change is a cause of rivers drying up and river and groundwater levels dropping. For several decades, nature has been central to my work, as it has revolved around building forest roads, levees along rivers, and logging. My continuous experience with water and soil has helped me realize that there are three unequivocal causes for the dropping river and groundwater levels, and by extension, for the desiccation of streams and forests. Namely, these are as follows: compacted soil areas, even at minimal grade, especially in the forests, that expand thousands of kilometers each year. Man-made slopes over compacted soil areas, we disrupt billions of soil capillaries each day. Drainage canals and lowlands. All three interventions might seem inconspicuous in themselves, yet they sprawl astoundingly fast and set off a disastrous process. They drain the landmass, which in turn overheats. Compacted soil areas. Most commonly, they are created by heavy machinery operating in intact forest vegetation, mainly during timber harvesting on forwarding paths. During log skidding, one forest tractor can compact up to 3 kilometers of forest soil, 3.5 meters wide, or 1 hectare in a single day. Rainwater or meltwater cannot infiltrate the compacted soil and reach the plant roots, springs, and groundwater. Instead, compacted soil routes the runoff water swiftly to lowlands and subsequently to oceans. In recent years, soil compaction and forest drainage has accelerated multifold. We have significantly increased the use of wood as a renewable source of energy in supplying the wood chips to the heat and power plants. When the logging process is complete, no one is charged with a task to restore the compacted soil to ensure the rainwater can infiltrate the soil once again. And yet, soil in this condition does not produce any vegetation for decades to come. To compound this effect, it also intensifies the runoff, which in turn strips the topsoil. All that remains at the end of the process is eroded rock that reduces the chance for new vegetation to a zero for several centuries. Here is another example. Soil that was compacted 50 to 80 years ago during horse skidding is covered in a 30-centimeter layer of rotten leaves and wood. Rainwater or meltwater still do not infiltrate the ground. The volume of runoff from rain and snowmelt increases due to the sprawling slope compaction, especially in the forests. The forest will lack the water in springs and summers. This scene shows intact forest soil that does not get soggy even during rain or snowmelt. I have been monitoring the condition of the Carpathian forests in the Ukraine and in Slovakia for several years. I have visited many places in Europe affected by floods, including the Polish forest, Jezirskie Hory in Bohemia, and the mountains over Genoa, Italy, near Dublin, Ireland, in Macedonia, and in St. Lawrence in the Austrian Alps. Lately, I have been to Lourdes in the French Pyrenees that had been hit by a flood. I was surprised to find a dense network of forwarding paths in the forest there. What caught my eye even more was a 10-kilometer asphalt road that stretched above the tree line, across a grassy area, and finished under cliff formation. High, man-made slopes above the road drained the mountain readily, as we witnessed when we got caught in the rain. The rainwater from the capillaries flowed out through a roadside ditch to the valley, then the rivers and the ocean. Again, I saw for myself that compacted soil and the slopes above them cause rapid landmass drainage. Man-made slopes. As we make artificial slopes, we disrupt billions of capillaries, which store enormous amounts of potable water and function as distribution channels to groundwater systems, springs, all plants. The water that flows out of the capillaries oozes down the compacted soil or a ditch under the slope. Drained capillaries in the slope are like ruptured supply pipelines which cannot serve their purpose. Human intervention in the landscape has turned the natural system that is meant to retain water into a drain pipeline, which causes the landmass to desiccate instead. The disrupted capillaries channel the water from rain and snowmelt instantly from the landmass to the seas and oceans. Topsoil in forests and forest meadows filter water from rain and snowmelt readily to the capillaries in deeper layers of the earth. For this reason, forest soil freezes only in places that were compacted by heavy machinery and human activity. It is clearly visible near the log yards in the meadows. Here you can see how much meltwater flows through the soil filter in the capillaries. If we sever them, they will discharge water, which will flow down the forwarding path or the ruts carved by the heavy machinery. The same process takes place during sustained or heavy rains. The compacted soil drains the rainwater instantaneously, compounded by water discharged from the severed capillaries, much quicker than during the snowmelt. Muddy water that oozes down the compacted areas quickly fills the mountain streams and rivers. Not only does it flow away into oceans through the concrete tiled streams and regulated rivers lined by high levees, it also floods out towns and cities. Judging by the huge quantity of muddy water in our rivers, we try to compensate by building even higher and stronger levees, or reservoirs and polders. However, it is imperative that we start with the flood prevention measures in the mountains, because the drained mountains already struggle to maintain the functions that are crucial for sustaining life on planet Earth. We decided to do an experiment and create slopes in several areas in a forest without compacted soil in the older vegetation. We divided intact soil over the edge of a slope into 4 test fields, 1 square meter each, as high as the double height of the slope. We simulated 200 meters of rainfall at a speed that ensured the water gradually infiltrated the ground without runoff. The simulation lasted up to an hour. We collected the water that the disrupted capillaries discharged in a test field within 3 hours in receptacles. From the overall volume of 800 liters, the soil absorbed 239 liters, and the remaining 561 liters, or 71.1%, flowed out through the capillaries. The discharge of the rainwater from the severed capillaries in a slope depends mostly on the height of the man-made slope, its grade, and the soil composition. In another test field, in the same mountain situated in an area without a man-made slope, we simulated a 200-meter rainfall within 3.5 hours. Once the simulation was over, we dug in and found the water oozing out from capillaries 40 centimeters deep. In other test areas of clay and stone composition, the simulated 200 millimeters of rainfall infiltrated within an hour. Then we dug in we found no trace of water. During this year's spring floods, some sources claimed that there was not a single river catchment in Slovakia that could contain 200 millimeters within 24 hours. I agree. River catchments contain intolerable amounts of compacted soil or soil drained by the disrupted capillaries in man-made slopes. I estimate that the drained soil over a slope is 3 times the width of the compacted soil under the slope. This drawing illustrates the compacted soil in black, empty capillaries in a man-made slope, and drained soil over the slope in brown. During the floods in 2010, some scientists acknowledged the fact that approximately 0.5% of the forest soil was compacted. After the flood near the town of Pila in 2011, a team of specialists led by Dr. Orfanus from the Slovak Academy of Sciences found that there was a 10-kilometer area of compacted soil on 1 square kilometer. They focused on forest roads, forwarding paths, and log yards. At an average estimated width of 4 meters, the compacted soil took up 4% of the area. That was 10 times more than what the scientists acknowledged in 2010. Circle number 1 depicts 100% of forests, with the estimated 0.5% of compacted soil. The drained soil takes up 3 times as much, or 1.5%. Circle number 2 shows the results of soil compaction measurements. I detected 7 to 10% of compacted soil with a GPS next to dried up forest streams. Graph number 3 illustrates the drained area in the forests, which takes up approximately 40% and keeps growing. When I arrived at these conclusions based on my experience, I started asking myself the following questions, intent on finding the answers. Question: why does it rain less in summers than it used to several decades ago? Answer: because the overhead air that rises from the landmass tends to keep the clouds coming from the seas and oceans out. Local vaporization over landmass that is systematically depleted of water has been dwindling. Question: when the clouds manage to reach the landmass, why do they tend to accumulate over the mountains? Answer: the hot air that rises from the overheated lowlands keeps the clouds out over the cooler mountain areas. Question: why was this phenomenon not noticeable 40 or 50 years ago? Answer: in the past, the lowlands were not drained by the man-made canals. In summers, the air that was rising up was saturated with water vapor from the soil, which also made it cooler. Drainage canals in the lowlands. I was born in the lowlands between 2 rivers, Ondava and Laborec. There were no drainage canals around them. In the late 1960s, a 4-meter deep canal at Sliepkovce was dug out among the first ones in eastern Slovakia. In the first year, the water level in the canal was 2 meters high. In the second year, when we were net fishing, the water level dropped to 1 meter. When I returned many years later in 2012, the canal was completely dry and overgrown with trees. I discovered that just between Ondava and Laborec, drainage canals running hundreds of kilometers were put in. The construction of canals disrupts capillaries on both sides, and they discharge the water they contained. Disrupted capillaries, much like the drainage canals, cause the surrounding fields to desiccate down to the baseline of the canals. After the heavy autumn rains, I measured the influence of the 3 canals on groundwater in an old well between December 2012 and May 2013. The measurements were taken at the lower end of the main K1 canal before its outfall at 101 meters above sea level. When the measured water level in the canal at Sliepkovce was at its highest, and the water from the stream called Dusha spilled out onto the fields, just 15 kilometers upstream of the canal and the stream at just 5 meters above sea level higher, the canal was nearly empty and the stream was merely half full. Other tributary canals were only partly filled in the upper parts. In winters, the water in canals, much like the groundwater, would rise and fall. During heavy spring rains, the rhythm of rising and falling sped up 5 times. The recorded measurements have shown that the 15-kilometer canal unequivocally affects the groundwater levels and its tributaries along its entire length. Water drainage in the lowlands is similar to the process in the forest, but there is one difference. This process started over 50 years. Looking at the warming trend of the atmosphere since 1860, I ascribed the steep rise of the temperature aberrations between 1950 and 1980 to the lowland drainage canals. Something analogous is happening in the forests. Rigorous use of the conveyor belt and wheel logging equipment since its boom in 1980 has produced a sprawling network of forest roads and forwarding paths. We have already started experiencing the impact. The diagram of truth. With regard to the trend of rising atmosphere temperatures and the trend of falling river water levels, the correlation with soil compaction, marked in black, and soil drainage, marked in brown, becomes apparent. If we did not channel the rainwater over compacted soil and disrupted capillaries, would landslides be so frequent? Would the river water levels keep dropping? Would the underground water levels be dropping? Would the streams keep drying up? Would the forests keep drying up? How about nature on the whole? No! Our landscape would not desiccate and the landmass would not overheat. If the overheated landscape were not warming up the atmosphere, would the icebergs keep melting? The ocean water mass in the southern hemisphere is 14% larger than that in the northern one. If the ocean levels rise in the north, they do so in the south as well. Larger ocean mass means millions of tons of water more. Does the planet's center of gravity shift? How does it affect the Earth's rotation? What other disasters can this phenomenon cause in the future?
An verdichteten Böden und die künstlich angelegten Hänge bedeuten eine Katastrophe. Es ist ein Auslöser für den Entwässerungsprozess des Festlandes, wo das Wasser schneller abfließt, als es während des Drehens des Planeten zur Sonne seine lebensspendende Funktion erfüllen kann. Das Festland trocknet durch Überhitzung langsam aus und die Welt muss steigenden Temperaturen und immer häufigeren Wetterschwankungen standhalten. Ich biete eine Lösung, wie dieser Trend aufzuhalten wäre und die negativen Einflüsse gemindert werden könnten. Diese Lösung ist sofort wirksam, einfach und nachhaltig. Die Eingriffe habe ich im Jahr 2011 an 2 Orten im Osten der Slowakei überprüft. Nicht genutzte Rückwege, Spuren nach Maschinen und verdichteten Bodenflächen habe ich über die gesamte Länge und Breite quer gegen den Hang und Wasserstrom aufgewühlt. Die Bagger haben den verdichteten Boden im Wald von der höchsten bis zur niedrigsten Stelle zerwühlt. Dadurch haben wir erreicht, dass das Regenwasser in den von den Baggern geschaffenen Gruben aufgehalten blieb. Waren die Grübchen frisch ausgegraben, blieb das Regenwasser darin an einigen Stellen auch längere Zeit stehen und sickerte allmählich in die Erde ein. Das bedeutet, dass sich das Wasser kleine Kanälchen geschaffen hat, neue Kapillaren und zu den Wurzeln von Pflanzen und ins Grundwasser durchgesickert ist. Beim Beobachten, wie sich der zerwühlte Boden verhält, fand ich im Frühjahr 2013 Wasser in höchstens 15% der Grübchen. In den anderen Grübchen sickerte das Wasser sofort in die Erde ein, sowie im ungestörten Wald. Wenn es über den verdichteten Flächen künstlich angelegte 2 Meter hohe Hänge gab, so haben wir sie ca. 1 Meter in die Tiefe des Hangs zerwühlt und das aus den Kapillaren abfließende Wasser sickerte in den zerwühlten Boden im Hang ein und allmählich in die vom Bagger geschaffenen Grübchen. Die Fähigkeit zerwühlter, verdichteter Flächen, das Wasser effektiv aufzufangen, wurde auch von der Slowakischen Akademie der Wissenschaften einer Messung unterzogen. Das Experiment wurde auf einem verdichteten, erodierten Weg gemacht, der früher mal für den Abtransport von Holz aus dem Wald genutzt wurde. Die Wissenschaftler haben einen Regen mit einer Intensität von 100 mm in 3 Stunden simuliert. Während der verdichtete Weg fast gar kein Wasser absorbiert hat, hat der mit Maschinen aufgewühlte Weg laut Messungen bis zu 100% der Wassermenge aufgefangen. Lösung des Problems künstlich angelegter Hänge. Mein Vorschlag für den Umgang mit den Waldwegen, die zum Transport beim Brandlöschen genutzt werden, sowie den Wegen, Straßen, die zum Transport von Rundholz mit LKWs genutzt werden, ist folgender. Das Erdreich graben wir auf in einer Breite von 1 Meter, in die Tiefe ca. 2 bis 4 Meter entlang der Höhenlinie in einer Entfernung von ca. 5 bis 20 Metern über dem künstlich angelegten Hang. Durch die Unterbrechung der Kapillaren sickert das daraus abfließende Wasser in den aufgegrabenen Boden ein und langsam auch in die Kapillaren in den unteren Schichten der Erde. Lösung des Problems von Entwässerungskanälen in Tiefebenen. In den Entwässerungskanälen in Tiefebenen schlage ich vor, kleine Betondämme mit einer Öffnung zu errichten, durch welche die Höhe des Wassers im Kanal und dadurch auch die Höhe des Grundwassers reguliert werden könnte. Dieses Verfahren habe ich im Jahr 2010 realisiert. Die nach 2 Jahren Monitoring ergriffenen Maßnahmen haben ihre Rechtfertigung und Funktionsfähigkeit bestätigt. Das sind Aufnahmen aus dem Sommer 2012, der sehr trocken war. Der Wasserpegel im Kanal ist genauso hoch wie das Wasser in einem 100 Meter entfernten Brunnen, was bedeutet, dass dieser Kanal sich daran beteiligt, das Grundwasserniveau stabil zu halten und die Brunnen mit Wasser auffüllt. Dieser Kanal ist leer. Der 70 Meter weit entfernte Brunnen hat einen Wasserpegel von 24 cm Höhe. Der leere Kanal führt allmählich das Wasser vom Brunnen ab, anstatt dass er ihn auffüllt, bis sich die Pegelhöhen ausgleichen. Ich habe mehr solcher Messungen an verschiedenen Orten vorgenommen. Alle haben den direkten Zusammenhang der Wasserhöhe im Kanal und den Wasserpegel im Brunnen sowie den des Grundwassers bestätigt. Dort, wo es gelingt, durch Regulierung das Wasser im Kanal zu halten, haben die Brunnen kein Problem mit wenig Wasser. Ihre Pegel sind stabiler. Ein Kanal ohne Wasser wird jedoch zum Feind von Grundwasser, da das Wasser aus ihnen langsam abführt. Einfache Lösungen sind sehr oft effektiv. Paradoxerweise ist es so, dass sie sehr schwer durchzusetzen sind. Lösungen, die wir direkt unter der Nase haben und die die Natur respektieren, müssen mit Geringschätzung kämpfen. Wir ersetzen sie mit komplizierten Bauwerken und Spekulationen über allzu viele Niederschläge oder globale Erwärmung, die wir angeblich nicht beeinflussen können. Ich bin überzeugt, so wie wir der Natur geschadet haben, so können wir auch helfen. Wir können tausende kleiner, finanziell nicht aufwendiger Eingriffe realisieren, deren Endeffekt riesig sein wird. Fangen wir das Wasser dort auf, wo es fällt. Lassen wir es nicht unkontrolliert abfließen und stoppen wir so die Austrocknung des Westlands. Geben auch Sie, so wie ich es tat, einfachen und vernünftigen Lösungen, die der Natur eigen sind und die die Katastrophen minimieren können, eine Chance und Spielraum.